Okay, hello, this is Bob Jackson. I'm here to go into chapter 17, the Earth's atmosphere and weather. This is for SE 202, fall semester 2022. Okay, anyway, this chapter is on mainly the structure of the atmosphere, and then we'll be talking the very base concepts for weather. Okay. In which this is in your weather is in your standards and earth science standards. Okay, and it's important to get kids to understand, particularly safety and what to do when you have different types of weather moving in, and it's different for different people. Like we're in Indiana, we don't worry any too much about hurricanes, but we do have to worry about tornadoes, and there's certain things that should be done, and that's what we do in schools with tornado drills and things like that. But students should be also aware of what they should do when they're at home or when they're outside, or live a normal life, and tornado warnings and stuff coming about. So anyway, we talked just a little bit about that toward the end of the PowerPoint. We will start out with talking about the atmosphere, the structure of the atmosphere. And then we'll go into wind just a little bit, talk about wind patterns, where the wind comes from, what causes wind. And then we'll talk some about weather patterns, and then end with the tornadoes and hurricanes. Okay, so here we go. Okay, the structure of the atmosphere. Here's the main layers of the atmosphere. We have the troposphere, the stratosphere, the mesosphere, and the thermosphere. We spend our lives pretty much in the troposphere. Okay, if you go flying in a jet, you're going to get out most likely into the lower part of the stratosphere. We like our commercial jets flying in that part of the atmosphere because it tends to be less turbulent. Okay, you can have, particularly where you have clouds and so forth, in the upper part of the troposphere, it can get somewhat turbulent. And even in the summertime, when you're getting a lot of warm air lifting and getting the turbulence. And that's where, when you're flying, when you're going, after you've taken off from the airport and you're going up through the troposphere, you can get where you get to upward air movement and you feel the turbulence. Okay, so anyway, the troposphere is the main part. We'll spend probably the most time talking about the troposphere because most of the things that we need for life comes from the troposphere. Okay, in the stratosphere, temperature increases with height, whereas in the troposphere, it gets colder as you go up through it. Okay, and people don't even feel that when you go up a mountain. Okay, but in the stratosphere, as you get on up in, it's hot up here. Okay, but the all the things we need for life, the gases, oxygen, and so forth, is all in the troposphere, but that starts changing as we go on up through the stratosphere and the mesosphere. Okay, the mesosphere is the highest layer where we have a good mixture of gases, but they're all mixed up. Okay, and they're not layered by their masses. Okay, the thermosphere is the hottest layer, and that's what I have on here. It can be up to 4,500 degrees Fahrenheit. That is hot, and that's what, with our space shuttle and so forth, has gone into outer space, where it's had to been built to be able to come back down through the heat without the tiles on the outside of it deteriorating. That is one of the biggest challenges, and where we had the we lost a shuttle because of that. Okay, because it's got to be able to endure that heat. Okay, now then, the other unique thing about the thermosphere, because it is such a thin part of the atmosphere, and you don't have air molecules like you do in the lower part, in the lower layers, sound doesn't travel. Okay, so you can scream all you want there. You can be outside an aircraft, and the sound's not going to travel because sound needs molecules to travel. Okay, but also in the thermosphere is where a lot of our satellites are orbiting and the space station is orbiting the Earth. Okay, so anyway, these are the main layers: the troposphere, stratosphere, mesosphere, and thermosphere. Okay, now the composition of the atmosphere. Okay, now then for the most part, we're talking just the troposphere part of the atmosphere on this. Okay, because it is quite different when you go on up. You wouldn't have 78% nitrogen on up in the upper layers of the atmosphere by any means. Okay, but the main three gases that make up the lower part of the atmosphere, the troposphere, is nitrogen, oxygen, and argon. Okay, and we need that oxygen at 21%, and if it falls much below that, people don't really tell. Okay, and that's where in Indiana, when people that have breathing issues, chronic breathing issues, or have emphysema, when get a lot of humidity, it's hard to pull the oxygen, hard for them to pull the oxygen out of the air. When the oxygen is just there at 21% anyway, but then you get a whole lot of moisture in there, it makes it tougher for them breathing. So, and that's where difference, and then people with chronic breathing problems a lot of times live a better life in some drier areas like Arizona or New Mexico and even southern part of Colorado, where you don't have near the humidity. Okay, but key things to know and to teach kiddos is 78% of the air is nitrogen, which is a good thing. And lightning gets involved with nitrogen and putting nitrogen back into the soil to help our plants. Okay, so that's where lightning is actually a good thing. Oxygen, I just talked, and then we have some argon, and that's actually where they can actually get argon to use for different things industrial. Okay, not very much there, but there is argon in the atmosphere. And then all the other gases, even though we hear about greenhouse gas and all, are at lower percentages, and it doesn't take much like carbon dioxide put in the air to change the characteristics of the atmosphere. Okay, and that's what you get to talk about when you're talking greenhouse gas and so forth. And we may talk in a later unit. We won't spend much time on that in this, in the weather unit. Okay. Atmospheric pressure is one of the most important measures we can take of the atmosphere. We use a barometer to use this. There are also instruments called anemometers, but the main instrument used is a barometer. Okay, whether it's a barometer or anemometer, we're always measuring gas pressures. Usually, if you hear the term anemometer, is for measuring one gas in a container. Like if I want to measure the, like when you have a pressure gauge on like an oxygen tank, it's really an anemometer. Okay. Whereas a barometer is measuring pressure of just the atmosphere. Okay. Atmospheric pressure is typically measured in inches of mercury or millimeters of mercury. Okay. As far as most scientists, and the standard for scientists is going to be millimeters of mercury, whereas in everyday life and on the weather, typically you're going to hear it as inches of mercury, like 29 inches of mercury. Okay, whereas in science you're going to see it as millimeters of mercury, and typically it's going to be like 700 or 800 millimeters of mercury and higher. Okay, now where that comes from is, and I have the explanation up here, is if you take mercury and put it in a glass tube and turn it upside down and put it in a bowl full of mercury, then air pressure pushes down on the bowl or bulb. Actually, what we'll put in the barometers is how you have a bulb on them, but it started with a bowl. Okay, but pressure pushes down on that mercury, and the force with which it pushes down on the mercury determines how much mercury will stand in this tube. And all we do is measure the height of the mercury. Okay, so if you measure to be this would be 760 millimeters, which is 76 centimeters. Okay, and then 29.92 inches. Okay, then that's what that measure is from right there to the top of the mercury in the bowl down here. Okay, and that's the measure. That would be the measure of the atmospheric pressure at that given time. And realize this changes from day to day, from hour to hour, and as the weather systems move through, because it's the atmospheric pressure that drives all of it. Okay, the weather systems. Okay, now we have went away from mercury barometers and mercury thermometers as well because of the hazards of mercury. The newer barometers have aneroid cells and springs, and that they're coiled springs, and the pressure will push on these, and that will determine the measure, how hard it's pushing on the either aneroid cell or the springs within the barometer. So if most of you have a barometer at home, it's probably either got an aneroid cell, which it's a cell that pressure's pushing on and making something happen. The harder the air pressure pushes on it, the more it's going to make the spring action take place within it to change the scale. Okay, but that's what barometers are. So now then, when we talk barometric pressures or atmospheric pressures, you can the terms are pretty much synonymous. A barometric pressure is an atmospheric pressure always, okay? But if you're talking high pressure systems, you're talking typically clear days, okay? Nice clear days, and you have the air dropping, okay? Whereas low pressures, you typically have the air rising. I think I got it on the next slide. Let me see. Yeah. Okay. So here is a low pressure. You got the air going up. Okay. That's converging air, lifting. That's going to cause moisture to be taken upward. And then that's where you get your big old clouds formed. And these great big clouds that form the anvil tops like that, those are cumulonimbus clouds. You'll start out with cumulus clouds. Okay, but that's low pressure systems, and you form your fronts. Okay, what we'll call cold fronts and then storm fronts. It's just all according to how much energy is in it and how much moisture is in it to determine what's going to happen weather-wise. Okay, how rainy it's going to be, how much of a storm it's going to be. And the higher these clouds get, the bigger this gets, typically the more powerful the storm is. Okay, high pressure systems is diverging air. The air's falling. It's more dense. Okay, and it's diverging outward. Okay, now then, other terms that you use for these, like the low pressure systems, are cyclonic effects, and anticyclonic effects are with high pressure systems. Okay, and that's where you see a total different movement of the air in each one of them. Okay, but a key thing to know is high pressure systems are typically not clear days. Okay, they can be hot or cold. I mean, you can have it in the wintertime. But they are clear days, whereas typically when you get your low pressure systems moving in, you're starting to see some clouds, you're starting to see weather develop. Okay, so, and that's where you start seeing terminology also here is unstable weather. Okay, and it's because this creates the instability. Okay. Now, wind is totally driven by barometric pressure readings and differences from one point on the Earth's surface to another. So on this map on here, you see out here toward Montana and the Dakotas here, I have a high pressure system. Okay, now that reading's 1024 millimeters of mercury, okay, which is pretty high. Okay, so they're having clear days there. But then down here in Florida, you see low pressure system in place down here. Okay, so now then we're here in Indiana. Okay, with this high here and this low here, then what's tending to be going on is you always have air movement from high to low. And the air movement is wind. So your winds are going to be going from the high to the low. So like here in Indiana, we'd have northwest, the wind coming from the northwest here, okay, on this particular day. So the weather system would be driven this way. Okay, now then, the distance between these isobars, you call them, okay, these are readings of air pressure. Okay, they're round, they're always cyclonic like this, or anticyclonic actually on a high. Okay, but you always see them in circles. Okay, because you have this region all measuring the same air pressure, this measuring the same air pressure, and so forth. Okay, and you call these isobars, and this is what our meteorologists or meteorology readings are going to be, and they have barometers and weather stations scattered throughout the country to take these readings, National Weather Service and all kinds of other entities anymore, NOAA. Okay, so wind from here to here. The distance between these determines how strong the wind's going to be. This wouldn't be too bad. This wind is would be rather light winds because there's a lot of space between the isobars. The closer these get together, the stronger the winds are going to be. Okay, so the key things to remember here is wind always moves from high pressure to low pressure. These are isobars that you see on the map. That's what we want to try to teach kids when they're looking at a weather map. They can see and they can start telling things themselves before the weatherman ever says anything. The closer these are together, the stronger the winds are going to be. Okay, so let's go to another one. Okay, on this one, we see a little bit more action going on. We got a low here. We got the isobars closer together. There's going to be relatively strong winds here. Okay, coming from this way, going towards the low. Okay, the high pressure is sitting out here towards or over the Four Corners area, Colorado, New Mexico, Arizona, and Utah. Okay, so the wind pattern is going to be here, but now here, it's not, the winds aren't too bad. Okay, but I mean, there would be probably light winds here. But as I get up here to the New England states, it's pretty windy up here. It's still driven pretty much from this direction, from the southwest, but it's going to be pretty windy. Okay, and they're most likely looking at stormy conditions there. Okay. Okay, and that's, I mean, that's pretty much it out here. You know, very little wind. Okay, nice space between the isobars. Lots of wind. Okay. Now then, when this is where we start getting climates developed and also wind patterns on a global scale. How they tend, like if you're from Indiana and you spent your life in Indiana, you realize our weatherman comes from the west. And if you want to pick out any direction the wind comes from the most, it comes from the west. Well, there's a reasoning behind that. If you take each of these areas on the earth, and this is where we talked the latitudes before. Here we have the equator. Here almost we have the Tropic of Cancer. Okay, and then the Arctic Circle up here. Okay, each of these regions are being differentially heated by the sun, with the concentration of the sun's rays here more than anywhere. In the summertime, we'll get more concentration up this way during our summer. In the winter, we'll get more concentration down here. Your Tropic of Cancer and your Tropic of Capricorn. Okay, and as a result of this differential heating of the Earth's surface, you get these developed. You get the easterlies, the westerlies, and the trade winds. Okay, the easterlies are where you're getting wind more predominantly from the east to the west, and that's like up in northern parts of Canada. Okay, and even Alaska. Okay, you have the same down towards the South Pole. Okay, now there's not as much land masses down here at the South Pole besides Antarctica as there is up here in the northern hemisphere. But these are the easterlies. Where we are, we predominantly get the westerlies. And that's why our weather patterns typically come from the west. Once in a while, we'll get some up from Florida and so forth with things that change, but it's a temporary. Okay, it's a storm front because of the high and low pressures weather set up. The predominant weather's determined from the westerlies. Okay, and then the tropical regions of the world and the northern part of South America and even over parts of Africa, okay, you get the trade winds. Okay, and they will blow predominantly from east to west. Now, that doesn't mean every day they do, but the predominant patterns are. That's why we also see whenever they're giving the weather about hurricanes, how the most impactful hurricanes getting Florida and down in here are typically coming in from this direction. Okay. But these are the global wind patterns. Okay. So it's a good thing to teach kids. You got the easterlies, the westerlies, and then the trade winds. Trade winds are in the tropics. Okay. And then we talk air masses. Air masses is what carries the weather more than anything else. Okay, and that's where you get in regions, and there's no reason to memorize these, and these can change with time. I mean, some of them stay predominant, but particularly these out here over the ocean, because they're going to carry in our major moisture. Okay, here, and here, and here, as far as bringing any moisture into the United States. Canada is famous for getting us the cold weather dropping down. Okay, but air masses will sit over regions of the earth for given periods of time. The longer they sit over a given area, the more they become like that area. Okay, so like this, and we're saying this, like you have this air mass here, it's picking up all kinds of moisture off the ocean here. Now, the amount of moisture it picks up is totally dependent on the weather at the time and how warm it is and so forth. Okay, but it's picking up that moisture, and then that weather is typically like this is showing moving this way. So it's going to bring that moisture in to the United States, into the land masses. Then it will change as it comes across the country based on the land it's over at the time. So come out here to mountain, it's awkward how much moisture it could rain out up here. That's where you get Seattle area and so forth. They tend to get quite a bit of rain as compared to us. Okay, because it can all rain out there before it ever gets carried on through here. Okay, because it loses those characteristics as it comes inland. Okay, just like we can get some really big storms at times in Indiana whenever we get the moisture pulled up in a low pressure system from the Gulf. Okay, because these air masses, they're large uniform bodies of air that pick up the moisture. Okay, particularly when they're out like in the Gulf or over the Pacific Ocean and even out in the Atlantic Ocean. That's like Hurricane Ian that we just had was this. Okay, it come from here. Of course, it picked up all kinds of moisture, and then it got a very become a very big storm, of course. But they drive, these air masses are what drive all the weather. Okay, so it's something important to teach kids, and they see, and you get to see in predominant weather patterns that take place, and like we're moving into winter, and since the sun's rays are moving more down towards the equator concentrated, then you get more influence of this guy. Okay, where we can get that cold air dropping down out of Canada and affecting us big time. Okay, and we're just starting into that pattern. Okay, warm and cold fronts. Okay, I think it's good to understand warm and cold fronts. A cold front, okay, you got cold air moving this way. The direction of movement of this front across the country or across the state or across an area, okay, is this way. But now then on a cold front, warm air is rising up over the cold air. Okay, so as the weather pattern's moving this way, the warm air's climbing over. The lifting of that warm air is what creates these clouds. Okay, And you get the cyclonic effect. You can form a cyclone. Ultimately, if it's out over the ocean, you can form a hurricane. Okay, and if you get significant lows within these, of course, you can form on land are tornadoes. Okay, so cold fronts, warm air over cold air, you get your clouds build up. They build up these great big old cumulonimbus clouds. That's where you're going to get your storms. Warm fronts, okay, the weather's moving this way. Okay, so it's moving that way. Okay, and the cold air is still down underneath here. So you keep those clouds up there high and you're not building up that turbulent air. Okay, so it's typically pushing the weather, it's pushing any of the bad weather out. Okay, it's the way I always look at it, because the warm air is going to have the biggest influence. Okay, so the warm air is going this way up over this, and this is moving out. Whereas a cold front, when a cold front moves in, you get the cold air and the warm air is rising up over it, and it's going to cause the action. Okay, as that cold air moves in underneath the warm air. Okay, this is all moving this way. The cold air is not moving under the warm. Okay. Okay, thunderstorms usually develop in warm, I've already kind of talked this, in warm, very moist, unstable air. Okay, in some of the storms, you get your tornadoes, which can be extremely violent. Okay, tornadoes are the smallest, most violent weather disturbances I can talk, disturbances on Earth. They are very low pressure centers. That's what's gonna cause them, and they get the funnel cloud that drops down out of the clouds, and it's the winds, tremendous winds around that very, very low pressure cell that's right there that causes the damage. Okay, because remember, whenever you get very, very, very low air pressures, that's where you get very, very high winds, and that's what a tornado is all about. Okay, hurricanes, on the other hand, are massive and they form out over the water. Okay, so you will see the big old cyclonic effect of it, where you see a cyclone cloud like that, and in the middle is the eye. That is the lowest atmospheric pressure of it, and how low that is determines the biggest characteristics of the hurricane, how strong the winds are going to be. Okay, which this is actually I stole this offline. This is Ian, as it is moving towards Florida here this fall. Okay. And then here's some EF ratings for tornadoes. EF ratings go from 0 to 5. Okay, we have very, very, very few 5 tornadoes. Of course, the higher on the scale you go, the much more violent that they are. Okay, and here's some, no reason to memorize this, just kind of show an EF0 is it's a tornado with 65 to 85 miles per hour. A lot of structures will withstand it. Might get some stuff blown off roofs, some tree limbs down, and some trees down, but not typically that bad. But once you start in the EF1 and on up, you can start getting some significant damages. By the time you get EF3 and 4, they're pretty violent. I mean, they can bring structures apart. Okay, EF4s are very violent, and EF5s are massive and incredible damage. It's just like having a very bad hurricane. Okay, but the biggest difference is tornado is going to have typically a narrow swath across an area, but you can get to where you get more than one tornado forming in a system that causes mass destruction. Okay, and then your category of hurricanes here, they're ranging from 1 to 5 also on this scale. You get up above 5, you're 155 mile an hour winds and greater. Okay, but a big thing with hurricanes is totally different than your tornadoes. You can get flooding and so forth, but it really has nothing to do with the tornado. Hurricanes, of course, they're occurring occurring in coastal regions is this storm surge that can be very devastating. I mean, wind is bad enough the way it is, but when you take islands and coastal communities that take 13 to 18 feet of storm surge, a lot of destruction. Okay, so that's where Ian hit Fort Myers, Florida, this fall, and it's the worst I've ever seen. Mass destruction. Fort Myers Beach and Sanibel Island, the Sanibel Causeway, is bad, and that's one of me and my wife love it down in that area. So anyway, your categories of hurricanes run from 1 to 5, 1 being the lowest and 5 being the highest. And that's a good thing to teach kids, but a big thing to teach kids about hurricanes is having knowledge of the fact hurricanes a lot more than just wind. It's storm surge, because you're getting massive waves coming in off the ocean, but it's not only coming in, but it goes back out. And a lot of them will tell you that water going back out you think it's over and it's not. Okay. So anyway, that's hurricanes, and that's my version of weather. So have a good week, and I'll see you with the next chapter.